So once again, my name is Sean Rothenberge. I'm going to be talking about multimodality flow analysis in cerebral aneurysms, but I'm going to be focusing a little bit more on how we can actually assess the error of our 4D flow MRI measurements. And so with these in vivo 4D flow MRI measurements, we're able to assess the velocity fields within our cerebral aneurysms. Alternatively, we can use modeling techniques such as computational fluid dynamics or in vitro 4D flow MRI to get this velocity information. And so with this velocity information, we can derive flow parameters such as wall shear stress or oscillatory shear index, which has been shown to relate to aneurysm progression. Unfortunately, all these modalities have their own sources of error that we have to consider. For one, for in vivo 4D flow MRI, it suffers from inferior resolution in both space and time. There's going to be variations across individual cardiac cycles, and there's also going to be low velocity to noise that we have to deal with. Additionally, for modeling modalities I just mentioned, we're going to have error associated with those boundary conditions that we prescribe. We're going to have to segment the geometries, and so there's going to be error in this domain. And we're also going to be making assumptions with the fluid properties. However, all these different modalities contain information about the true flow. So the idea is if we can understand the error of each modality, we should then be able to fuse these modalities together to estimate this flow. And so with this information, we should then be able to attempt to eliminate the error from our measurements. We can also use this within our machine learning applications, as discussed by Dr. Vitaly Reyes and Hemanth on Wednesday. And in addition to that, we can use this to actually derive weights, which we're going to use in the future to fuse these modalities together. And so what I'm going to be discussing today specifically is I'm going to introduce two different methods which we can use to approximate the error of our 4D flow MRI measurements, specifically spatially. One of those methods is going to be by using our understanding of the imaging physics. I'm just going to be going over the theory for today. In addition to that, we're also going to be applying our understanding of the fluid dynamics that are taking place to estimate this error. I'm going to be discussing the theory along with some results that we currently have for a phantom study that we performed. And so first, before I get into the describing how we actually calculate the error, I'm going to introduce how we actually look at the error within our voxel. So we look at it as a superposition of our true velocity along with a bias error and a random error, and that's going to be what our measurements actually are. Currently, there is literature on what this random error is influenced by. It's a function of our VANC along with our signal-to-noise ratio. However, currently there's a gap in our understanding of what this bias error actually is. And in particular, right now I'm focusing on this bias error due to voxel averaging. So the way that we're modeling this bias error due to voxel averaging is we're thinking of it as the difference between the true velocity, which exists at the center of this voxel, along with what we're actually measuring, which is the integration of all these true velocities at all positions A within the voxel limits. We then divide by this total velocity, or this total volume, to get our voxel average value. We can then approximate our true velocities within this voxel using a three-dimensional Taylor series expansion. After we substitute that into this first equation that I mentioned, we're going and making a second order approximation. We're going to be left with this equation for our estimated bias error, which you'll see is a function of the second order derivatives in all three components of our velocity component. This is done on individual velocity components, along with the individual voxel dimensions. And so right now, this is a theory that we're working with. We're looking to apply this in the future to in vitro and in vivo 4D flow measurements. Additionally, I also mentioned that we can use our understanding of fluid dynamics to estimate the error of 4D flow MRI. Specifically, we know that mass is going to be conserved both globally within our measurements of the flow, along with locally within each individual voxel. What this means is that the divergence of our true velocity field is going to be 0 as long as our flow is incompressible, which is a safe assumption to make for blood. Also, what we can say is that the divergence of our measured velocities is going to be equal to the divergence of our total error that we see here. And so what we're going to do is we're going to use this equation then to estimate the error of each voxel for our measurements. And so as I mentioned, we also applied this to a phantom or an in vitro study. And so we are provided with time of flight data along with in vivo 40 flow MRI information from our collaborators at Northwestern University for this internal carotid artery aneurysm. We segmented it, and we have this unscaled geometry that you see here. We also scaled it up by a factor of 2, and I'll discuss why we actually scale it up in a few slides. Then we are able to 3D print these flow phantoms. We inserted these flow phantoms into our flow loop, prescribed a steady flow because we're only trying to understand the error spatially. In the future, we'll look at error temporally as well. And we also place these flow phantoms within our scanner. We imaged each aneurysm model individually at the exact same spatial resolution as you can see here. We also used a dual Vanc 40 flow MRI sequence developed by Dr. Schnell at Northwestern, and so we were able to simultaneously acquire measurements at 2 separate Vancs. In addition to that, we repeated our measurements a total of 18 times for each individual model. And so with this, we then calculated the error for each voxel using this divergence method that I just went over. And we are looking at the effects of our resolution of the flow along with the SNR and the Vanc. And so as you can see here qualitatively, although we didn't actually change the size of the voxels, with increasing the geometry size, we're able to better resolve the flow fields within the aneurysm. And so what we found with an increase of, as we averaged more of those repeated measurements together, we would expect that the SNR would increase as well. We see that our error variance dropped with an increase of SNR, which is what we would expect. And in order to calculate this, we basically just took the error of each voxel and calculated the variance for the entire, calculated the variance for the entire geometry. We also looked at the effects of the spatial resolution, and we saw that with the larger geometry or the higher resolution of the flow, we saw a drop in this error variance. And last, we also saw that with our lower Vanc acquisition, we also see at all SNR values, we see this lower error variance. And so in conclusion, I just spoke about 2 different approaches that we can use to look at the error of 40 flow MRI. I looked at the relationship between this error and Vanc SNR and resolution based on this fluid dynamics approach to calculate the error. And in the future, we want to expand our understanding of this imaging-based error approach, apply both error methods to pulsatile flow, and also implement these error estimates so that we can then fuse our different modalities together. So with that, I'd like to thank you for your time. I want to acknowledge our lab along with our funding source. Thank you.